Greetings, everyone. Welcome back into some more Calc 2 on infinite series. We're now crossing the threshold from basic series into some of the stuff that we're actually using series to accomplish. We're going to talk about power series. A power series is whenever you have a variable like x inside of an infinite series that's indexed by some other variable like n. Okay, so a lot of times we equate these with some sort of function. So I could say that my infinite series is n is going from 0 to infinity. That's my counting index variable. And then a sub n is just some other sequence that I'm making a part of the series. And then I've got x raised to the power n also. Now you'll notice that it's minus c, and that's just because I'm being generic. These things can be shifted on a value of x. And we call the value c that we shift this on, we call that the center of the series. Okay, but the main point is that it's x to the n power. X is some continuous variable. X can take on any value, whereas n is an index. It's a counting variable and will only take on positive integers, and 0, right? Depending on what you put in your sigma notation there. Okay, so that's what a power series is. We're now involving another variable. Okay, however, that variable being continuous gives us a lot of other options that we weren't doing with series before, including the ability to turn it into a function. Being able to create a series is being able to create whatever functions we want, basically. It's like being able to build one. Okay? And also, having a variable in there allows us to give some variety in there, because depending on the value of x, the series will either diverge or converge. And that's actually a lot of what we need to talk about in this lecture. Depending on what value of x we're using, will the series converge or diverge? Okay, so here's some examples of some power series right here. I have the sum from n going 0 to infinity, x to the n power over n factorial. So in this case, the a sub n, the other part of the sequence there, is just the 1 over n factorial portion. Okay, and then x is not subtracted by any numbers, so the center is technically 0. And this series just looks like this: 1, x squared over 2, x cubed over 6, so on and so on. Okay, so that's a power series centered at 0. Here's another example. Negative 1 to the n plus 1 over 3n times x plus 2 to the n power. Now notice here I have x plus 2, whereas the generic stand was minus something. So my center is actually negative 2 because it's minus a negative. Okay? This is a shift to the left on the x-axis, if you will. And then, of course, the sequence being the rest of it over there, the negative 1 to the n plus 1 over 3n. And this is an alternating power series, you'll notice, because of the negative 1. It does alternate in sign. Okay? Just like all of the other things that we have the different categories of these things. Okay? It's mainly important that you see that a power series is not just any series with x involved. It's a series that has x raised to the power of the series index variable. Okay? It's not the summation of sine of x. It's not the summation of the logarithm of x. It's literally always going to be a summation, and x is going to be raised to the n power. Okay, so don't get these things mixed up. It's not any series with x in it. It's specifically using powers of x. Okay, and we have a couple of reasons for this. One, basing it on powers of x gives us a direct connection to a lot of the types of series we've already been using. Powers of x also give us a series like this that's basically a polynomial. And what this is going to show us eventually is that we can take any function and approximate it with a polynomial series. Having polynomials, complicated polynomials are just that. They can be complicated, but polynomials are the simplest family of function. And being able to relate everything into polynomials is a very powerful tool, especially for approximations. Okay, so the other, like I said, the other part of this lecture, we need to focus on when these series converge. Okay, so because x is a continuous variable, the value of the x is going to matter, and we're going to have some sort of interval of convergence. An interval of convergence is a region of x values that cause your series to converge. And what we do is we start by computing a radius of convergence. So you need to picture, we've got the center, okay? We can compute the center just by looking at the series. And once you're at that center, your radius is going to tell you how far left and right you can go of that center, and the series will still converge. Okay? Now let me qualify. The series is always going to converge at the center, but that's a trivial convergence, because think about it. If I plug in x equals -2 here, right? -2 plus 2 is 0. It zeroes out everything, right? And right here, if I plug in 0, it zeroes out everything. So the center is a trivial convergence point. It's always going to be there because it basically is going to zero it out. So it's an uninteresting convergence as well. It just means your series is equal to 0. Okay? But if you can compute a radius of convergence, then from the center, you can go a distance on either side, like this. And once you go to either side of the center, you actually get an interval, c minus r to c plus r, of convergence. Okay? So I've already shown you two different possibilities here. What if your radius is 0? Then you're only going to converge at the center. That's guaranteed. You will always converge at the center. Okay? In which case your interval of convergence is not actually an interval. Notice I have the squiggly braces. Your point of convergence in that instance is just the value of your center, c. Okay, so x equals c, basically. If you have a radius, some number, okay, then you will have an interval where you do the center minus the r, the radius, to the left, and the center plus r, radius, to the right. So you will actually have an interval, okay, where all of the values in that interval will cause convergence if you plug them into x. And then there's the other possibility that your radius is infinite. If your radius is infinite, that means the series does not depend on x to converge. It converges for all values of x, in which case your interval of convergence would be -infinity to infinity, or you could write it as x exists as a real number, or x is an element of the real number system. Okay? So those are the three different possibilities we're going to be expecting here. Okay? Some of them will not have a radius of convergence. Some will have a finite radius, and some will have an infinite radius. But it all is based off of the center that you can read, and then how far out that interval of convergence reaches. Okay? So this is like the bare minimum of what you need to know about a power series. Once you are issued a power series, or once you create one, you need to know, hey, where does this thing converge? What values of x cause this to converge? And that's what we're going to be computing, the radius of convergence, to apply and create an interval of convergence. So let's get a clearer idea of what I was just referring to about finding the interval of convergence. So it'll be kind of at the same time. We'll be calculating the radius of convergence and the interval of convergence. And it's important to know the connection between the two when you're solving these things. Okay, so I've got three different power series here, and it's important for you to note that they are power series because they each have x to the n power. right? X to the n power, x to the n power, okay? So when you approach one of these power series, it's important to note the center. X is not added or subtracted anything here, so I'm going to go ahead and say my center is 0. Now, once you've noted that, we want to try and find the interval and radius of convergence, or radius and interval of convergence, whichever way you want to look at it. Okay, now the way we do that is we test the series all together for convergence. Typically, this is done with either the ratio or root tests. However, you can take other ones into regard. However, the existence of absolute convergence is helpful with these because it does allow for an interval to go in both the positive and negative directions. Okay, so with this one, I'll show you how we can use both and you'll get the same result. So let me start with the ratio test. So with the ratio test, remember what we're doing is I'm taking the limit as n goes to infinity of the n plus 1 term times, actually it's divided, right? Divided by the original term, which means I'm going to do the reciprocal here. So I'll have n factorial over x to the n. Okay, so remember what I'm doing here is I'm actually doing a n plus 1 divided by a n, right? And this is a sub n right here. So I've flipped and multiplied. I've done the reciprocal to inhabit the division there. Okay, so then I'm going to reduce this limit as n goes to infinity of the absolute value. And then here I've got x to the n plus 1 over x to the n. That's going to leave me with an x. And then I've got n factorial over n plus 1 factorial. Okay? Don't forget, n plus 1 factorial is really n plus 1 times n factorial. So with this one, I'll be able to just wipe out the n factorials, and I'm just left with n plus 1. So this is over n plus 1, like so. Okay, now also, there's one other thing that we need to say. We need to say that for a ratio test to give convergence, this limit needs to be less than 1. Because remember, equal to 1 would be inconsistent or inconclusive, right? Greater than 1 would be divergent for a ratio test. So I'm going to use the limit here less than 1. And this is the statement that I want to find a solution for x. Okay? So I take the limit as n goes to infinity. And since it's just n in the denominator, x is just some number compared to n. Well, that's going to go to 0. I'm getting that 0 is less than 1, which is always true. Since it's always true, this is one of those cases where the radius of convergence is infinite. Think about what always true means. It means that x could be any number, and this limit would always give me 0 no matter what number x was. Okay? So the limit as n goes to infinity of this, I get 0 is less than 1. This tells me that my interval of convergence, my IOC, is where x is an element of negative infinity to infinity. And my radius of convergence is going to be infinite. Okay, my radius is unbounded because it didn't really matter in this case where my center was. It's the whole number line. Okay, so right here, because of this statement, that tells me that my interval of convergence is that. So in other words, for this particular series right here, I could put any number I wanted to in for x, any number at all, and this series would actually converge to some value. For every value of x, doesn't matter. Okay? Now what about root test? I could do the same thing with the root test. The root test says take the limit as n goes to infinity of the nth root of the absolute value of a sub n. So I have xn over n factorial, like so. Okay, so then the absolute value portion is still going to space out the way it did before. I'm going to have the limit as n goes to infinity of the absolute value of x over the nth root of n factorial, because I can split the root between the two, right? And remember, for the root test, it has the same stipulations as the ratio test. This limit has to be less than 1. But the limit as n goes to infinity of the nth root of n factorial is infinity. So I've got x over infinity basically, right? And then this is going to have the same result. 0 is less than 1, which is always true. Okay, so I could have used either one of those tests and gotten to the same result as before. Okay. Now, the next one here. For this next one, I'm going to go with the ratio test again, especially at first. First, I'm going to note what the center is, right? My center is -2. Because that's what would zero this out, okay? Now don't forget, it's definitely always going to converge at the center. I also need to figure out if there's a slight radius away from the center, or if it's infinite like the last one. Okay, so I'm going to plug in the ratio test again. And that's going to be the limit as n goes to infinity. The absolute value is going to knock off the negative portion. Okay, I'll go ahead and write it. N plus 2. Because it's n plus 1 plus 1. I'll go ahead and write that out. Over 3 times n plus 1, and then it's x plus 2 to the n plus 1, and it's divided by this. Okay, so times the reciprocal here. I'm going to have 3n. I'm going to have -1 n plus 1, and I'm going to have x plus 2 to the n. Okay, so that's dividing by the original a sub n term here. Of course, all of the negatives are going to go away because of the absolute value, so I'm not worried about those. And then I've got x plus 2 to the n plus 1 over x plus 2 to the n. Okay? Now, don't forget, when you're doing division, right, you can just subtract those powers. So I'm getting the limit as n goes to infinity of the absolute value of x plus 2. Okay, so notice right here, right, I'm going to have an x plus 2 left over. And it's important that I kept the absolute value this time, because x can theoretically try to be any number. So this could be a negative, in which case the absolute value does have some effect. Okay? So the absolute value knocks off these negative ones for sure, the multiplied ones, but I'm going to keep it on x. Now n is guaranteed to be a positive number because that's our counter. Okay? So I'm going to leave those alone, And then also notice 3 over 3 also reduces. And so I'm left with n over n plus 1. So times n over n plus 1. That's that limit. Okay, now remember this limit, whatever it happens to be, is supposed to be less than 1. Okay? So then in the next step, I go ahead and take the limit. The limit as n goes to infinity doesn't affect this piece. So that piece is still there. But the limit as n goes to infinity of n over n plus 1 is 1. So I'll have times 1, which is just itself, is less than 1. That's this statement. So here we go. This is a statement about x right here. This is an inequality with an absolute value, which, if you haven't been trained or if you've just forgotten, you can actually read this as a center with a radius. Notice the center is exactly what we've been reading, right? Center is -2, and 1 is the radius. Okay? Anytime you have a less than with the absolute value like this, that's one way of interpreting what you're getting. Okay, so what I'm actually getting is an interval of convergence that's centered at -2 and has a radius of 1. Okay? So then, to continue to solve this, you can rewrite it like this. -1 less than x plus 2 is less than 1. Okay? And then I'll subtract 2 from all 3 sides, which tells me -3 is less than x is less than -1, but that's really not the way you want to read that. It's telling me that I have an interval of convergence between -3 and -1. So that's what I would put for my interval of convergence. But hang on. Before we just go down writing it out, I'm going to start it, but I'm not going to finish it yet. Interval of convergence, I'm going to have x is an element of, and I'm going to have -3 comma -1. But should I put parentheses here or should I put brackets? That's another question entirely. I must test those endpoints. So before I put these parentheses or brackets in there, okay, we actually must test this out to see if they're actually included or not. Because what happens? If I put equals on here to put the bracket, remember the ratio test is going to say, well, that's inconclusive. It doesn't diverge, it doesn't converge necessarily. I just don't have enough information when it's equal. So what we do is we actually take the cases where it's equal and we test them individually. There's only 2 cases. If I plug -1 in for x, or if I plug -3 in for x, the 2 endpoints would be where the equals part would be. So I'm going to test both of those locations to check for convergence. Okay? So to do that, I'm going to make myself some space here first of all. Or you know what? Actually, I'm okay. I'm going to block this off and give myself some space is what I'm actually going to do. Because I don't need much space for this next one. Okay? Like this. So now, test the endpoints. This is important. Once you find an interval of convergence that's finite, or a radius of convergence that's finite rather, you must test the endpoints. What that means is, when x equals -3, plug it in and we'll see what you get. When x is -3, I have the sum n equals 1 to infinity, -1 to the n plus 1 over 3n, times -3 plus 2 to the n, like this. But -3 plus 2 is just -1, okay? So I have n equals 1 to infinity. I have negative 1 to the n plus 1 times negative 1 to the n over 3n. Well, remember, these are the same base. I can add the exponents, right? So n plus n plus 1, right? Okay. So then this is giving me the sum as n equals 1 to infinity of negative 1 to the 2n plus 1 over 3n. Okay? So look really closely. I want you to see right here the negative 1 power is to the 2n plus 1. That's important because n is a whole number, always, right? That's our counter. And 2n plus 1, 2 times a whole number plus 1, is always odd. This is always an odd number. Well, negative 1, that's always to an odd number. That's just negative 1. So what do I get? From this, I get that this is the sum from n equals 1 to infinity of negative 1 over 3n, which, if I factor that out, is just negative 1/3 times the sum from n equals 1 to infinity of 1 over n. And hopefully from here, you'll recognize right away this is a p-series, and not just any p-series. It's the harmonic series, and it's divergent because the p is not bigger than 1. Okay? So, recap. If I let x equal negative 3, I can show for a fact through p-series that this endpoint is not included in the interval of convergence because it diverges when x equals negative 3. So I put a parenthesis there. Okay, next, what happens when x equals negative 1? Okay. When x equals negative 1, we have the sum, n equals 1 to infinity, negative 1 n plus 1 over 3n times negative 1 plus 2 to the n. But what's negative 1 plus 2? That's just 1. 1 to the n is still 1, right? This value right here is just 1. And anything times 1 is itself. So what does that give me? That just gives me this thing without that part in it. I have negative 1 to the n plus 1 over 3n. Okay? Well, again, I can factor the 1/3 out, like so. N equals 1 to infinity of negative 1 to the n plus 1 over n. And you'll notice now it's not just a p-series. It's an alternating series, but also a p-series. Okay? And we've seen that one before. That's conditionally convergent. Okay? What's the condition? The condition is as long as you have the alternating, it converges. Okay? So this converges. By alternating series. Okay? So I'm hoping you're seeing how having those skills of all the other basic series before is coming to fruition. You need to know what happens in these individual cases when I plug in a value of x. Certain ones need to be tested. Okay? When I plug in the x equals negative 1, it stays alternating. And therefore becomes convergent by the alternating series test. So I would put a bracket on this guy right here. That one's got a bracket. While the other one, plugging in negative 3, made the alternating go away. And therefore diverged by p-series. So my interval of convergence for this series is x can be any number in between negative 3 and -1. But it cannot be -3, and it can be -1. Okay? Remember what that means. I can plug any number I want in between there. Any number. You plug that in for x, it will be a convergent series. Okay? So if I had some function f of x is equal to this, if I plug in and ask what's f of 0, you would say doesn't exist. But if I say, hey, what's f of -1.5, right? That's on this end. You'd say, oh, well, I can find a value for that. And then maybe you'd have to approximate it or whatever. You'd find some way to sum up and get a value for that series. Okay? So in other words, the interval of convergence is kind of like a domain for this function. These are the values of x that when I plug them into this x, I can actually get a number result out of this infinite series. If you happen to have an infinite interval, like all real numbers, I can plug in any number and get a result for the series. Okay? Some of them have finite radius of convergence. Okay? In which case I've got some sort of interval that I have to find. And then there's this third case. Let's talk about this third case right here. In this case, first thing I'm noticing is that my center is 0 because there's nothing added or subtracted with the x. Okay? And I'll go ahead and use the root test on this one. You could use either one. I could have used the root test on the one earlier. Remember, both of these are interchangeable as long as you can do the limit. So the limit as n goes to infinity of the nth root of the absolute value of 3n factorial times x over 5 to the n. Okay. So 5 doesn't have a negative, so I can kind of let that one hash out. But then notice x to the n and 5 to the n, the nth root is going to wipe those out immediately. And I'm just left with the limit as n goes to infinity of the nth root of 3n factorial times the absolute value of x divided by 5 because of the nth root with this piece. Now the limit as n goes to infinity of the nth root of just n factorial is infinity. Right? Okay. So basically this limit right here is infinity. I want this to be less than 1. Remember, that's the test. I want this to be less than 1. Okay? I'm not actually going to give the statement infinity is less than 1 because that's never going to be true. This is one of those cases where if you run into this situation, I'll write it, but let's not dwell on it. Infinity is less than 1 is false. So what's the solution? Well, if you just put any old number in for x here, then it's just going to be some number times infinity, right? In which case you'll get infinity is less than 1, which is always going to be false, with only one exception. If x equals 0, then we'll get 0 is less than 1, which is true. Okay? Now think about this. Infinity times 0, that's one of the biggest arguments in all of the limits, like infinity times 0 is indeterminate. This isn't even a contest of infinity times 0, because look at what's happening. If I let x equal 0, then every single term is 0, right? Because if I zero this out, 0 divided by 5 is 0, and then 0 times any number, 0. So you're just adding up 0, 0, 0, 0, 0. Okay? So my radius of convergence is non-existent. Okay? I only have a single solution to this inequality. To this inequality right here. Only if I plug in the center. Okay? If the center happened to be something else, like up here it was -2. Right? Plugging in -2 would have zeroed it out. Here, it just happens to be plugging in 0 because that's my center. Okay? So there is no interval of convergence. Okay? Only converges at the center. X equals 0. That's an important property to know about a power series. Okay? Every single value of X diverges on this series except one value. And it's a trivial convergence. So this doesn't seem to be a very useful infinite power series, right? I can't plug in any other values of X, and the one value that I do plug in gives me nothing but zeros. So it's just equal to 0, right? So it's kind of trivial. There might be a circumstance where that's an important piece of information. For the most part, we like to have these two types of power series if we're going to study them as functions, okay? But you need to know that this happens, okay? That it only converges at the center. And as I said before in the last scene as well, the center is a guaranteed convergence. Every power series is going to converge as its center because of the way it's constructed, right? Because that's the only reason this one can converge there anyway, okay? Because it zeroes out all the terms. That's what the center does. Okay, the center of a power series, all the terms are zeroed out. But if you do have a radius of convergence, you'll have some sort of inequality that you have to solve, okay, with a less than, and it will be centered at the same center as the power series itself, and then you'll have to test the endpoints. Or you'll end up with something where the inequality is always true no matter what value X is. X gets wiped out of the inequality. Okay? Those are always nice, right? You don't have to test anything extra. Okay? But these are the three possibilities that can happen. Let's get a few more examples of power series so that you can see a little bit more. So here are a few more examples and even sort of some structures that you can look at when you're trying to determine the interval of convergence for these power series. Notice that if I have something of this format right here, where I have a number on the outside of a parentheses or bracket, and then a number on the inside times x minus c to the n, okay? K, P, and C are all numbers, and obviously C is going to be the center of the series. It is just x to some power still, okay? But this number K can actually be factored out of the whole deal. P is going to be raised to the n, and so is x minus c. What that basically boils down to is a geometric series. So in this case, I don't actually have to use the ratio and root test. We use the ratio and root test a lot because of the way x to the n doesn't work with very many other things. But in this case, since it's just a few numbers multiplied by the x minus c, or just x to the n, I can actually treat this as a geometric. And what this avoids is having to test the endpoints of the intervals of convergence. Because if I can show that this is definitely a geometric, which it is, it's just a number raised to the n, there's no n's anywhere else, okay? Then geometric series don't converge when the equal to portion is available, okay? Geometric series just don't do that. So what you basically have is that P times x minus c is your R of the geometric series. It's the object being raised to the n power. So if that's true, the absolute value of that R has to be less than 1 for a geometric series to converge. Okay? Then also, that means that I would have to have x minus c absolute value less than 1 over the absolute value of p. Typically, p will be positive, but it doesn't have to be. In which case, the inequality can be solved by splitting it over the less than of the absolute value, and I have the negative 1 over p and the positive 1 over p, well, absolute value of p. And of course, I'll just add the center, and I'll get an interval of convergence that's anywhere from c minus 1 over p and c plus 1 over p in size. Okay? So, what actually falls into those categories? Let's look at a couple of examples of this particular structure. Look at this guy right here. The sum from n equals 0 to infinity of 4 times x minus 5 to the n over 9 to the n. It doesn't exactly look like that yet, but we can manipulate it. Notice the 4 does not have any relationship to the n whatsoever. So that would be like our k. The 9, however, is to the n power. So that's going to be part of the p, the number that's kind of on the outside, but still to the n power. And then, of course, I have x minus 5 to the n. Okay? So I can rewrite this series right here as the sum from n equals 0 to infinity of 4 times 1 over 9, and I'll use a bracket, times x minus 5 to the n. Okay, so when I rewrite the series like that, it's just 1 over 9 to the n, you see, and x minus 5 is still to the n. But then this is exactly a geometric series where all of this number right here is my r. So I can proceed to solve it the way that this is listed out here, in which case the absolute value of 1 over 9 times x minus 5 has to be less than 1, which tells me that the absolute value of x minus 5 has to be less than 9. So x minus 5 would have to be in between negative 9 and 9. And if I add 5 to all three quantities now, then I will get negative 4 is less than x is less than 14. And I know I don't have to check the negative 4 and the 14. I know this is very similar to some of the ones we did in the last scene, but remember, I'm actually using a different test. The way that I'm getting from here to this inequality is by geometric test, the geometric series test, which is stone cold about the equality. You can't equal 1. Your r cannot equal 1 for convergence. So I know that this is a geometric because there's no other n's involved anywhere else. It's just some number to the n power. Now sure, that number has my x in it, but it's still just a number when I'm looking at the variable n. And as long as x is in this interval strictly, not on the endpoints, as long as x is in this interval, then my interval of convergence is given as it. My interval of convergence is x exists in the negative 4 to 14 interval. Okay? Now, up here, if you'll notice this statement right here, you can see my center is 5, just as it's claimed here. You can see my center is 5. Center is still 5, and it has a radius of 9. Right? The radius is 9 there. The radius of convergence. But my interval of convergence is negative 4 to 14, strictly inside, right? No equality. Okay, what about this other guy? This one right here. You can see already that it's a geometric because it's some number to the n power there, okay? Some number raised to the n. If you want it to look like this format, then what you would do, and you don't have to do this, by the way, you can solve it straight from here, but this is what you would end up doing if you want it to look like that format. You could just factor out a negative 6, and you would have x minus 1 over 6, and then this would all be to the n. So you could actually treat it this way, okay? But you don't have to. You don't have to work it that way, okay? But look, this is what's going to happen. I'm going to do, I'll go ahead and treat it from here. It doesn't really matter which way you do it. Since I did the other one like that, I don't want to do it that way. Let me go ahead and just do it from the original statement. Okay? I just wanted to show you that it was parallel to the same thing, but you can tell that it's a geometric because it's some number to the n, as I said. So therefore, the absolute value of 1 minus 6x has got to be less than 1. Okay? Now, to make this more like what I need, I would like to have my x positive. Okay? Now, fortunately for us, the absolute value means that I can actually reverse it and still have the same result. Okay? An absolute value, no matter which way you do the subtraction, is going to be the same. Now, you can only do that with absolute value. Okay? I can reverse a subtraction, and the result is the same. If I divide everything by 6, then I'll have the absolute value of x minus 1 over 6 is less than 1 over 6. So then notice from here, what this is telling me is that my radius of convergence right here is the 1 over 6 right here. Okay, radius of convergence is 1 over 6. Okay, and my center is also x equals 1 over 6 by coincidence right here. Okay, this piece right here tells me that my center is 1 over 6. And if that wasn't obvious from up here, it's the same idea in both places. If I factor out the negative 6, it was x minus 1 over 6, remember? So I got my center from there as well. Okay, well, this I can solve by splitting. Negative 1 over 6 is less than x minus 1 over 6 is less than 1 over 6. And then I'll just add 1 over 6 to everything, and I'll have that it's between 0 and 2/6, which of course I'll simplify to 1/3. So my interval of convergence is going to be that x is a member of the interval from 0 to 1/3. And you'll notice I, again, did not test the endpoints. That's because of me, again, using the geometric series test, not the ratio test or the root test. Okay? When I was in the last scene using those particular tests, they are inconsistent at 1. The geometric series test is not inconsistent at 1. When your r is equal to 1, your series diverges in a geometric series. So you don't have to test the endpoints on those. That's a fun other way of looking at these. Okay? Now, of course, once you start going outside of that, then you go back to, well, I may have to do a ratio or root test. Okay? And then once you switch back to those, then you have to start testing endpoints. The sum from n equals 0 to infinity of the sine of x to the n over n. Okay, well, this isn't just x to a power. This is a sine function of the x variable. Okay? So this is not a power series. This is not a power series. So I won't be finding an interval of convergence for that particular series. That's not one of the ones that we'll be interested in. Okay? A power series, when you write it out, should be some polynomial. And this won't be that. This will be the sine of a lot of our variables in there. Okay, so that's not going to be a power series. Next, you'll notice this looks a lot like this guy right here, except now there's an n squared in the denominator. So I can't claim the geometric test anymore, because even though I could rewrite some of it like this, I can still do that. I could rewrite some of it. I can't rewrite all of it to the n power, right? The n squared is not part of a exponential feature. Therefore, this is not going to be strictly geometric. so I can't use the geometric test on this particular. I'm going to have to fall back on either the ratio or root test. I'm going to opt for the root test. Okay, so I'm going to test the limit as n goes to infinity of the nth root of 4x minus 5 to the n over n squared times 9 to the n. Don't forget, this actually has to be an absolute value of that, not just the term itself. Okay. I can split this up by terms of multiplication and division. Okay, so I'm going to have the nth root of 4. I'm going to have the absolute value of x minus 5. Because it was an nth power, right, with an nth root, that's just going to wipe those out. I'm going to have the nth root of n squared, and I'm going to have 9. Okay, now the limit as n goes to infinity of both of these pieces goes to 1. Okay, both of those go to 1. And therefore, since this is a root test, I want this to be less than 1. Okay, now note, that's exactly the same inequality that I solved over here. I'm going to end up solving this inequality where the absolute value of x minus 5 the absolute value of x minus 5 is less than 9. Because I'm solving this inequality, I'm going to multiply both sides by 9. Therefore, I've got a center of 5 and a radius of convergence of 9, exactly like I did over here. So I'm going to solve this inequality the same way as I did over here, and I'm going to get an interval of convergence starting out as x being in between the -4 and 14. Right? Same as over here. But I can't say that that's my final issued product because I didn't use the geometric test this time. I used the root test, which is inconclusive at 1. All right? That means that I need to test the individual pieces. Okay, so my starting interval of convergence is that. Now I need to test the two cases. When x is -4, what do we get? Okay, so when x is -4, I get the sum, n equals 0 to infinity, of 4 times -4 minus 5 is -9 to the n over n squared 9 to the n. Now -9 to the n and 9 to the n, those are both to the n power. I can reduce those. What I end up with is the summation from n equals 0 to infinity of 4 times -1 to the n over n squared. Okay, now this is an alternating series, but even without the alternating, I have 4 over n squared, which is a convergent p-series. Okay, so this converges. What about the other value when x is 14? When x is 14, I get the sum from n equals 0 to infinity of 4 times 14 minus 5 is 9 to the n over n squared 9 to the n. Well, notice these two are going to reduce, and I'm left with the non-alternating p-series 4 over n squared. So this one converged two different ways, right? This one's absolute convergent series right here. because with or without the alternating, it converges. This is strictly just the P series, and it converges. Okay? Now, of course, when you're working these problems and you have to do an actual write-up on these things, you're probably going to have to write actual statements, right? Like, I can see that this converges when x equals -4 by alternating series test, or by P series test. I can tell that this converges. So the overall interval of convergence here, the actual interval of convergence, is going to be when x is a member of, and I'm going to use brackets this time, -4 and 14 both get the bracket because both of them, when I tested, converged. Okay? All right. And then, of course, you have, when it starts going really outside, right, you have all kinds of crazy combinations. This is just something that you're going to have to find a way of doing. Well, you can always start with the ratio and root test, but I mean, sometimes you have to go outside, and it just depends on what you see. The thing you want to try first, usually, is either the root or ratio tests. So that's what I'm going to start with here. I'm going to start with the root test again. Okay, so I'm going to be taking the limit as n goes to infinity of the nth root of ln of n over n, and then x to the n. And don't forget there's an absolute value on that. Okay, so I'm doing the root test. So you would say by root test, right? This is true, which is going to be equal to the limit as n goes to infinity of the nth root of the ln of n divided by the nth root of n. Okay? Times the absolute value of x. Now, as you've probably seen in the previous lecture, you already know the limit as n goes to infinity of the nth root of n is going to be 1, right? It's actually the same argument that I used up here. The limit as n goes to infinity of the nth root of n squared is 1. Okay? You can make a very similar argument about the ln of n. Okay? ln of n is a value that's greater than 1 as long as n is greater than 1. But it's less than that. Okay? So by the same argument, the nth root of this is also going to go to 1. All right? As n gets larger and larger, the nth root is going to take over, and it shrinks anything larger than 1 on the polynomial scale down to 1. Okay? So this whole limit portion right here of all of this stuff is going to go to 1. And remember, this is the root test, so I would like to have this less than 1. So I'm solving the inequality where the absolute value of x is less than 1. And therefore, x is going to be in between -1 and 1, which is where I'm going to start my interval out at. So my interval of convergence, right? This is the meat of it, the middle. My interval of convergence is going to be where x is a member of the interval from -1 to 1. And I'm either going to use brackets or parentheses here. But remember, this isn't something that I did a geometric test or whatever. I did a root test, which is inconclusive at equals. So I've got to test the two individual series, right? So when x is equal to 1 and when x is equal to -1. Okay, so we're going to test these out. When x equals -1 and when x equals 1. When x equals -1, then I've got the series from n equals 1 to infinity. X is -1. So I have -1 to the n, which makes it alternating. ln of n over n. Okay? Now, the limit as n goes to infinity of ln n over n, the limit as n goes to infinity, and we've talked about this before, right? This limit is equal to 0 because n is going to be greater than the ln of n. Okay? Therefore, this converges by alternating series. Okay? So this side converges, which means I'll put a bracket on this one. Now what about when x equals 1? Well, in that case, I'm just going to get the sum from n equals 1 to infinity of ln of n over n times 1. 1 to the n is still 1, so I'm getting just this. Okay? We did a comparison on this one. Okay? ln of n is greater. This is true right here. 1 to infinity of ln of n over n is greater than 1 to infinity of 1 over n, because ln of n is greater than 1 as long as ln is more than that, right? As long as n is bigger than 1. So this sum is bigger than that sum, and we've actually talked about that one before. Okay? So this diverges. This is the harmonic series, which means this series diverges, which is the one we're interested in. So this diverges by comparison, by direct comparison. Okay? So this one diverges, which means I'm going to put a parenthesis on that. Okay? So here's my interval of convergence for this one. In summary, for these examples, it depends on which test I'm using. I'm hoping you're noticing this. I use the root test on these two, which is why I had to test the endpoints, because the ratio and root tests are inconclusive when it's equal. However, the geometric test is very clear cut. It does not use the equals ever. Equal to the one here is divergent. So I did not have to test the endpoints. Okay? We use ratio and root test a lot, but it's not our only option in some cases. Let's do two more examples. Sometimes they'll have a series like this where it'll be something based on a pattern, and you have to try and make the sequence out of the pattern that you see. So it looks to me like right now what they want is for us to multiply 1 over all of the odd numbers multiplied up to some 2n plus 1. And remember, 2n plus 1 is guaranteed to be an odd number as long as n is an integer. Okay? So this is just multiplying all of the odd numbers up to 2 times n plus 1. So it's going to start at 1, right? Because that'd be 0 plus 1. Then the next term would be 1 times 3. Then 1 times 3 times 5 would be the next one. So on and so on. So instead, I want to try and find a better way to symbolize this with the n's so that I can turn it into something that I can evaluate with our series tests. Okay, so here's the method that I used to do this one. I'm noticing that if I would just have the even numbers along with it, that this would become a factorial, right? If I had 1 times 2 times 3 times 4 times 5 times 6 times 7 all the way up to some value, that's just a factorial, okay? So if I were to multiply top and bottom by 2, top and bottom by 4, top and bottom by 6, right? And top and bottom by 8, on up, right? Times 8. And then I would want to stop at the 2n plus 1, but I'd have to be just before it, right? So 2n plus 1 just before it would be 2n. So all the way up to 2n. So I'm multiplying the numerator and the denominator by all of the even numbers up to whatever 2 times n is. Okay? So then that makes this n equals 0 to infinity. And my denominator is now 2n plus 1 factorial, x to the n. My numerator times 1 doesn't change anything. What I have is 2 times 4 times 6 times 8 on up to 2n, right? Okay. Another way of looking at those even numbers would be to think of each one as something times 2. So for the 2 here, this would be 2 times 1 times 4, which is 2 times 2, right? 6 is 2 times 3, 8 is 2 times 4, on up to 2 times n. Do you notice that since this is all multiplication, I could actually rearrange this? I could rearrange it where there's two times 2 times 2 times 2, and I could do this n times, right? Because there's 2, 2, 2, 2, all the way up to 2 times the n, but each one has a 2, and I'll just kind of rearrange the multiplication where I push all those 2's to the front. And then what would be left over? 1, 2, 3, 4, all the way up to n. Like that. Okay? So now what I have is that this is going to be equal to the sum, n equals 0 to infinity, of there's n number of these 2's. That would be 2 to the n times all of the numbers multiplied up to n. That would be n factorial over 2n plus 1 factorial, x to the n. Okay? So now I've got a representation with n for my sequence along with the x part of the power series there. And I can use one of my techniques, one of my series tests to test it, right? To check it out. So let's do that. I'm going to use the ratio test this time. Okay? So according to ratio test, the limit as n goes to infinity of 2 to the n plus 1, don't forget your absolute value actually on everything, 2 to the n plus 1 times n plus 1 factorial over 2 times n plus 1 factorial divided by this term, right? But don't forget to divide. I'm actually doing reciprocal and multiplying. So that would be 2n plus 1 factorial over 2 to the n times n factorial, like so. Okay, that's equal to the limit as n goes to infinity of, I can already reduce the 2's, right? 2 to the n is going to go away with this 2 to the n and leave me with 2 to the 1, right? So I have, oh, we forgot something. I hope all of y'all caught me. I completely forgot the x to the n. I should have x to the n plus 1 divided by x to the n. And technically x to the n plus 1 is here, and the x to the n came from here. But remember, all I'm doing is the n plus 1 divided by the n. So even if I did it in pieces, like each piece could do it that way. Okay, now I continue. Sorry about the little hiccup there. N goes to infinity. Absolute value. Everything is positive here except the x. Okay, so I'm going to have the 2 that's left over from here. And then I've got n plus 1 factorial over n factorial. I've got 2n plus 1 factorial over, now simplify this, don't forget it's 2 times n, which is going to give me 2n. And then 2 times 1 is 2, plus 1 is 3. So plus 3 factorial. And then x to the n and x to the n, remember these are going to reduce to give me x to the 1. But it's in an absolute value, and this is the one where it matters. So it would be times absolute value of x. Okay? So I'm still reducing this limit here. But let's do a little side work. Remember, n plus 1 factorial is the same thing as n plus 1 times n factorial, because it's just n plus 1 and every number before it, and n happens to be the number right before it. So I'm basically reducing all of the numbers except n plus 1. 2n plus 3, I would have 2n plus 3 times 2n plus 2 times 2n plus 1. And then the 2n plus 1 will be the factorial that will reduce here with this. So I'm left with 2n plus 3 times 2n plus 2 in this denominator here. All right. So then, as I carry on, I have the limit as n goes to infinity of 2 times n plus 1 over 2n plus 3, 2n plus 2 times the absolute value of x. And look at what we have here. If I do this right here, 2 times n and 2 times 1, that's 2n plus 2, right? So notice these actually reduce as well. So I'm left with the limit as n goes to infinity of 1 over 2n plus 3 times the absolute value of x. The limit as n goes to infinity of this piece right here, that's going to be 0. And remember, we want our evaluation to be less than 1. And this one always is. 0 is less than 1 is going to be always true. Right? Remember what that means. My radius is infinite. So my interval of convergence is where x is a member of anything from negative infinity to infinity in this case. So I don't have to check endpoints in this case because every number is included anyway. So now let's take a look at this problem. It looks a little bit different, but actually we can get away pretty easily still with the test that we've been using. Okay? So I've got x to the n cosine to the fourth of n, which means that I won't be able to do a ratio test very easily. Think about this for a second. What would happen if I were going to try to take the limit as n goes to infinity of cosine with an n plus 1 versus cosine with an n? Right? Because that's what the ratio test is going to do to you. So this isn't going to work out very good because we don't have many good ways of relating cosines with, or trigonometry is difficult in general, I should say, to relate to just about anything else. We use identities for all of that stuff. And there's not good identities for doing those kinds of ratios either. Okay? So the ratio test is kind of out. However, we can use the root test. Okay? So let's approach it that way. With the root test, I'm going to be doing the limit as n goes to infinity. Okay? And the limit as n goes to infinity of the nth root of x to the n times cosine to the fourth of n. Don't forget the absolute value, right? The absolute value. Now, this is going to be equal to the limit as n goes to infinity of the absolute value of x times cosine to the 4 over n power of n. Now let's talk about that for a second. Let me make sure you're with me. Don't forget I have the nth power and its absolute value in the x. Nth power, nth root just gives me my x. And then I have the nth root of something to the 4th power. Don't forget we can convert roots into fraction powers, right? So right here, what I have is the cosine to the 4 over n. It's the whole thing now, not just the cosine. This is shorthand, right? It's actually cosine of n. And then this whole thing is being raised to the 4 over n power. Okay? Now, another thing that you need to remember is that cosine, just by itself, is going to be between 0 and 1 in size, right? So if I do the absolute value, let's say, cosine in between 0 and 1 is going to be between 0 and 1 in size. If I take it to a power, 0 to the 4th, 1 to the 4th, same thing. I don't have to worry about the absolute value because 4th power takes off the negative. Still between 0 and 1. And I know what you're thinking. Wait a minute, doesn't cosine equal 0 and 1 sometimes? It does, but only when your argument is some multiple of pi, except for 0 itself. Cosine of 0 is 1, right? So that would be the only time you'd have the equals is when n is 0. For this setup, okay? Now, in general, for every other n, it would have to be some multiple of pi, and pi is not a counting number. N is restricted to being a counting number. So this is pretty much stuck as some decimal between 0 and 1, okay? Now, on top of that, you have to think about what the nth root, right? The over n is doing to this thing, okay? The nth root right here, as n goes to infinity, is basically saying that this is becoming the 0 power. So I've got some number. It's not 0, it's not 1, because we're going off to infinity, but it is some counting number, okay? So that's why it's never going to be 0 or 1. It's some number between 0 and 1. And basically, we're just saying that that number, right? This piece right here is just going to be some number to the 4 over infinity power. It's not actually infinity. We're not supposed to do that, right? The limit is doing that for me. 4 over infinity, right, is going to 0. I have some number to the 0 power. That's what's happening here. Okay? So what am I getting? I'm getting 1. I'm getting 1 as this goes on and on. Okay? Also, don't forget, the cosine itself wants to go to 1 as n goes to 0 anyway, but that's not happening with the argument. In any case, I'm getting that this is equal to this. And as per the root test rules, right, this has to be less than 1. Okay, so then that means that my interval of convergence is going to be where x is in between -1 and 1. And of course, we have to check the actual endpoints here. Okay? You're going to find pretty quickly that this is very closely related to like a geometric. It's not going to be able to be equal because it basically is a geometric just times a bunch of random decimals between 0 and 1. However, we do technically need to check them because we're doing a full-on, argument here. So my interval of convergence is going to be in between those two, and I just need to see the endpoints. So what happens when x is -1, and what happens when x is 1? When x is -1, I get my series from 0 to infinity there of -1 to the n. So it's an alternating series, cosine to the 4th of n. Okay? We can argue, actually let me go ahead and set both of them up because it's the same argument for both. If I plug in 1, I get 1 to the n, which is 1. So I just get cosine to the 4th of n. So here's the thing. I was able to do the limit of the cosine to the 4th when I had the nth root. However, if I do just the limit of the cosine to the 4th of n, that's really indeterminate. However, I do know that it is some number between 0 and 1, right? Because as this goes on, this thing will never hit 0 or 1, but cosine is trapped in between those two. Okay? So I know for a fact that this limit, even though it's indeterminate, I know that this limit is not 0. The limit of just the cosine to the 4th n. Okay, no nth root, just the cosine with the 4th power and the n itself. Hell, just the cosine of n. I know that it's not going to be 0. That right there tells me that both of these are divergent by nth term test. Remember that very first test we talked about with series, right? The limit of the sequence has to go to 0. So at x equals -1 and x equals +1, it cannot converge. Therefore, my interval of convergence for this guy is -1 to 1. So that one felt a little different, but you just had to be careful with which one of the tests that you want to apply, right? Ratio is really going to be too complicated. I even thought about using limit comparison. The limit comparison came up with a similar issue with this limit, though, being indeterminate. And so it's close, but no cigar on that one. Okay? So I hope this has shown you another variety on top of the one that we were just talking about. I know I had to erase it real quick in order to skip over to this one. Okay? One more thing to talk about, and is part of our purpose here, okay? Let's wrap up with a discussion of kind of where this is all going. Okay, remember, our whole point is eventually to start analyzing functions using these things. So let me give you a small introduction as to how I can take a function and actually rewrite it using a power series, so that we can use our knowledge of series to start, looking into more in depth of functions. Eventually, after we're done with talking about all of the things that we can about power series, we're going to, Taylor series, Maclaurin series are coming up on top of that. After we're done with all that, we'll be able to take any function and compare it to a power series some kind of way. Okay? But let's just start with an introduction. And that is, just a few of the basic crossovers here. And then we'll get to the more advanced stuff in the next few lectures. Okay, so here, what you want to notice is that I've got a few variety of functions, but most of them are fractions. Okay? First off, though, polynomial. Anything polynomial with x to powers, right? You may have already caught me mentioning this, and if not, this is the time to pick it up. A power series already is a polynomial. Okay, so if you have a function that's in a polynomial form like this, it's technically already a power series of a sort. This one just isn't an infinite power series. Okay, but if I really wanted to, I could rewrite this as the power series that looks like this. I could say that this is equal to the sum n equals 0 to infinity of a sub n x to the n. Okay? But then I have to qualify it, where a sub n equals 0 when n is not 3, 1, or 0. Okay? And a sub 3 is 3, A sub 1 is -2. A sub 0 is 7. Sort of a complicated answer, I know. Okay? But basically, the idea is this. I already have a sum of powers of x here, right? If I have x to the 0, that's 7. See, a sub 0 is 7, x to the 0. A sub 1 is -2, and then it would be x to the 1, you see? 0, x squared, so that's one of my, a sub 2 would be 0, right? Because 2 is not one of these numbers. A sub 3 would be 3. A sub 4 would be 0, a sub 5 would be 0, a sub 6 would be 0, all the way on up, right? Because all it is these three terms. I can actually just write it in this series, but really this is just a long drawn out way of already saying, hey, we've already got powers of x here. Okay, so it's sort of not a good use of power series to represent something that's already a series of powers of x. Because that's what we're trying to do with the power series. We're trying to take functions and write them as sums of powers of x. Okay? So that's why you won't see it used really on polynomial functions. I will make some parallels from time to time with polynomial functions to sort of give you an idea of where we're going with it. But polynomial is really where we're trying to get to with a lot of these things. We would like to get to polynomial functions because those are our most simple type of functions, and they're easy to approximate with sums like that. Okay? They're easy to graph, they're easier to find roots of and things like that, to find important features of. Okay, so the rest we're going to talk about are some rational functions here, because these are the easier kind to transfer into our normal power series. The connection is the geometric type of series. And actually that should make sense to you because the power series, x to a power in a sum, right? That basic setup screams geometric if it doesn't have ends anywhere else. Well, that would lead us to a lot of these type of solutions from the series, right? Think about it. 1 over 1 minus r in my geometric world, right? In fact, not just 1, but a over 1 minus r is equal to the sum n equals 0 to infinity of a times r to the n, right? That's our geometric formula for finding the sum of an infinite geometric series. Okay? So that means that a function that's already in that kind of fraction form can be written as a sum where you just have to make sure that you have a 1 in the denominator minus whatever you want your r to be. So I just need to rearrange these fractions a little bit to get that 1 and minus some quantity that I can call r. Okay? So then here's this first one right here. It's already in that format. I have an a, which in this case is going to be 1. I have this 1, and it's minus some quantity. So I can quickly just make this into the sum n equals 0 to infinity of 1 times x to the n. And that's it. There's my infinite series for this function. Okay? As you take on one of these things, you'll see how this can actually approximate some values of this function. Now, here's the kick. Not all values are going to be able to be done with this particular power series. This power series has an interval of convergence that's different than the domain of this actual function. But when this thing does converge, it does equal this function. Okay? It just doesn't converge for all of the values of that function. Notice the interval of convergence here is when x is in between -1 and 1. And I get that directly from the geometric series, right? Because x is my r, and x has to be in between -1 and 1 for it to be convergent. Period. Well, but the domain of this is everything but 1, right? The actual domain on this function is that x can't be 1. But it can be anything else, right? That's the domain of this function. The interval of convergence of this series is not the same as that domain always, and that's just because of the way infinite series works. If I want to approximate a different section of this function, then I need to shift my center. Right now I'm centered at 0, okay? So I'm just going to be trapped at something around 0. Some functions work better than others, and it just depends on the way it comes out in the formation. And we do have ways of shifting the center. We'll get there. But for now, with this one, as you can see, I do have a power series representation. Real quick, let's test it out, right? So what happens when x is 0, right? If I put 0 in here, okay, then everything is going to be 0 except for the first term. Notice that this series is equal to 1 plus x squared plus x cubed plus... If I plug in x equals 0, right, I've got 0, 0, 0, but look, 1. And if I plug in 0, I do get 1. Okay? And I know that's a trivial example, but you can see that these things are trying to be the same. And it's only going to be in between these two values. If I try to plug any other number outside of it, this will just be an infinite series that doesn't converge. And then, I won't be able to approximate it. Okay? All right, next. Right here, same idea. But notice I don't have the 1 right here. So that's important. What I'm going to do first is I'm going to divide by something that will make that happen. Okay? I'm going to divide by 4. Divide by 4. Divide by 4. Completely legal as long as you do it top and bottom and distributive property across. All right? So then this is going to be equal to 3/4 over 1. Now instead of plus, here's what I'm going to do. Minus negative x squared over 4. See, it's still x squared over 4, but the double negative has been unsimplified from the addition. And the reason is because I want a 1 minus. So that's what I have, 1 minus. So all of this, whatever it is, must be my r value. So then this has got to be equal to the sum n equals 0 to infinity of 3/4 times negative x squared over 4 to the n power. And of course I can rewrite this a couple of different ways. 0 to infinity. I can take the 3 and just sort of make it a loner. The negative to the n power would be the negative 1 to the n. X squared to the n would be x to the 2n. And then I have 4 to the n times 4. So that would be over 4 to the n plus 1. So that's another way of writing this same series that you could do. Okay, what's the interval of convergence on this one? Well, look at your r value right here, right? My r value is the x squared over 4. So therefore, the absolute value of the x squared over 4 would have to be less than 1, which would tell me that x squared would have to be less than 4. The absolute value is not necessary, but I'll write it because x squared is always positive. So for x squared to be less than 4, x has to be in between negative 2 and 2. So there's my interval of convergence there. Again, notice it's not the same as the domain of the function. Okay, this is my interval of convergence. The domain of the function is all reals because 4 plus x squared is never 0. So again, the interval of convergence doesn't have to match the domain of the function. And that just means that this particular series that I've made will approximate or equal out to a certain amount of the values of this function. And if I want to find out other ones, I just have to shift my center. We'll talk about that right over here in this next one, okay? So this, just this particular one is good for certain values. Just keep that in mind. Okay, so now that I've led to it, let's talk about it. What happens that allows me to shift a center? Let's say I have some function and I want the center to be a certain number because I want to have some interval around that particular center. Well, to do that, I just need something rewritten in a certain format. Okay, so remember, I'm going to have some number over 1 minus something in here. Okay, now that something in there just needs to contain, somehow I need to make it contain x minus 5. I need to make that happen in order for my center to be 5 and for this to be something that I can turn into one of those series using the geometric format. Okay? So to do that, I'm going to manipulate my denominator until I can cause this to happen. Okay? So I need the 1 there. That'll be like my last step. I can use division like we did over here. But I have to have x minus 5, which means I'm going to have to move around some numbers in the denominator by adding and subtracting some things. Okay? So here I go. Here's what we're going to do. I am going to rewrite this a sub x 6 over 2 minus x plus 5 minus 5. Okay, now of course you know where the 5 comes from. That's where my center is. And I'm paying particular attention to this little piece right here. And the reason why I wanted plus 5 is, remember, my goal is to get x minus 5. But the x already has the negative, you see. And I want to factor out a negative, okay, to make it an x. So that's why I put the plus 5 next to it. When I factor out the negative in the next step, okay, it'll come out of both of these because I want it to be one parentheses piece. So then I've got 6. I have 2 minus x minus 5 minus 5. Okay? I factored the negative out. So then my next step would be to just kind of combine whatever's left over, because the negative 5 and the 2, they're just both outside of that parentheses. I might as well merge them up. So that gives me 6 over negative 3 minus x minus 5. Okay, we're almost there. Remember, I wanted a 1 here for this particular piece. So I'm going to divide by whatever that is. I'm going to divide by negative 3 so that this will be 1. But that means I need to divide this by negative 3, and I need to divide this by negative 3. Okay? So then now it looks like this. I've got negative 2 in the numerator. I have 1. I'm going to keep this minus. I know, double negative. You're thinking I should have changed it to plus, but wait. Remember, I want a subtraction there. Okay? So it's 1 minus, and I'm just going to put a bracket here, x minus 5 over negative 3. Okay? I separated it out just so that you can see that's where my r is now. So my a of x can be rewritten as the series. Actually, I shouldn't call it the a of x because that's not the full function, right? It may not converge for every bit of it. But that can be shown to be somewhat equal to n equals 0 to infinity. Negative 2 is my beginning constant there, times the x minus 5 over negative 3 to the n. Right? My r raised to my n power. And of course, I can manipulate that into looking a little bit differently if you want. You can n equals 0 to infinity, right? I can pull my 2, and then this negative and the negatives in here can be merged. Think about it this way. I have -1 to the n, and then I have another -1. So it's -1 to the n plus 1, because I have n of them here, and then I've got one more. Okay? My denominator is 3 to the n, and then I've got x minus 5 to the n. Right? That's that piece. So it's just two different ways of writing the same thing. Just depends on how you want to look at it. Okay? You can see it is a power series because I have x at the end, and you see the center is now 5. Right? Okay, what about the interval of convergence on that one? Well, remember my r, the absolute value of it, so absolute value of x minus 5 over 3 has to be less than 1. Which means when I multiply by 3, absolute value of x minus 5 has to be less than 3. Which means x minus 5 would have to be in between -3 and 3. And then I add 5 everywhere. That would be that x would have to be in between 2 and 8. So my interval of convergence is x is a member of the interval from 2 to 8. Again, that probably is not the domain of the original function, although it is funny to see, right? 2 is not included. 2 is also an asymptote here. It should make sense, right? I better not be able to plug something in here, and it should not be equal to that then, right? Because this is undefined at 2. Well, so is the infinite series then. However, this has a domain that goes far beyond 8 and way on the other side of 2 as well. Okay, so I still only have a section of the domain there, but that's a pretty decent section depending on where you want to be. So as you can see, I shifted my center, and that gave me a different interval than I would have had I centered around 0, right? If I had centered around 0, I'd probably have something on the other side of that 2 asymptote, right? It would have been capped to stop at that asymptote if I'd gone all the way to center at 0, right? Whereas these are centered at 0. So then what if you've got something more complicated like this? We have several different ways of approaching that. I'm going to show you one of them right now. And as long as I can write it as some sort of parentheses, some sort of quantity where x is plus or minus something that I don't mind calling my center. They're not telling me to use any particular number as my center, so I'm just going to use whatever I can get, right? So here's what I'm going to do. I'm going to complete the square on that denominator because that will turn it into a parenthetical object, x plus or minus some value. Okay, and it'll also have a number plus or minus it on the outside. So I complete the square on this. That means that I take half of the 8 and square it, right? That should be 16. So what I'm going to do is x squared plus 8x plus 16 minus 5. 11 is 16 minus 5. All I did was I sort of, pushed out the other value there from this. I just rewrote 11 as 16 minus 5. And remember, the reason I did that is because now I can turn this piece right here into x plus 4 quantity squared. Right? That's what completing the square means. Okay? So then this becomes 9 over -5 plus x plus 4 quantity squared. Now I wrote it backwards, right? I put the -5 in front because remember that's what we're doing. I'm trying to get that quantity to be the same. And now I'm going to do my little division maneuver, right? Because that's how I get the 1 that I need there. I'm going to divide by -5 here, here, and here. Okay, so that now my b function is -9/5 divided by 1 minus x plus 4 quantity squared over 5. Conveniently this time, dividing by -5 gave me the subtraction that I needed here for my geometric formula. So now I'm going to say that this can be written as the sum from n equals 0 to infinity of 1, or no, let's just do x plus 4 squared. Whoops, forgot my a value. Negative 9/5 times x plus 4 squared over 5 to the n. Right? So then I could also rearrange this another way. I could also say that this is n equals 0 to infinity. I could say negative 9 times x plus 4 to the 2n power, right? And then that's all over 5 to the n plus 1, because I have 5 to the n, and then I have another 5 multiplied, so it's 5 to the n plus 1. Okay, so there's my series representation. It is centered at negative 4, right? You can see that that's just part of the way that I was completing the square. And of course, there is a way to shift the center. It's just all in the way you manipulate it. But in this case, they didn't ask for that. So I just went with whichever center was convenient for my process, right? In this case, negative 4 is my center. Let's find the interval of convergence, right? The interval of convergence is going to come straight from the r that I have, which is x plus 4 squared over 5. So x plus 4 squared over 5 has to be less than 1, which tells me that I have to have x plus 4 squared is less than 5. Okay? Then that means that x plus 4 has to be in between plus and minus square root of 5, right? And therefore, negative 4 minus the square root of 5 and negative 4 plus the square root of 5 is going to be what x is in between. Okay, so my interval of convergence, in this case, is going to be when x is a member of the interval negative 4 minus the square root of 5 to negative 4 plus the square root of 5. Okay, and then that's my series here. Okay, so I hope that this has given you an insight into what a power series is and some of the important details of power series, especially intervals of convergence, and then that we can relate power series to actual functions that we are going to be interested in analyzing. Okay, stay tuned. Next lecture, I'll give you a lot more of the details of the properties that we can use power series with that allow me to link even more functions into the power series themselves. So I just wanted to give you one other little snippet of a view of this. So what I have is of those functions that I was just talking about making the power series for, and you can see through these visuals how having these infinite series can actually approximate these functions and their function values. So the first one we're looking at here is the 1 over 1 minus x function is in blue. And right now a very, very poor approximation is y equals 1 plus x right here. So as you can see, it does actually approximate it. They are like one next to each other. It's a tangent line to it, but it merges with it right there. And what I'm going to do is I'm actually going to create it one term at a time. So y equals 1 plus x, that's the one we were just looking at. Look at what happens when I add x squared and x to the third and then x to the fourth. As you can see, every time I add a term, it starts merging more and more of the curve with a better approximation in a close region here. Okay, and you'll see that the amount is getting wider as well. The more terms that I add to this thing, the closer it gets to the infinity, which we're nowhere near there now, but the more terms I add, you'll see how it actually spreads closer to the actual interval of convergence, which is, in between -1 and 1 for this particular series. Okay, but the more terms I keep adding, x to the 7th, x to the 8th, x to the 9th, x to the 10th, I get closer and closer to the edges there, and you can see this is very, very close approximation, and especially right here close to the center. It's like right on top of it. You can't tell them apart with these two things right here. So that particular series is actually a good approximation for just this region of 1 over 1 minus x. Okay, so then that's the simple one. Let's look at the next one. 6 over 2 minus x. Right, and this is the one that we wanted to have the center at -5 over here. Okay, so we're going to be centered around -5. And this is a very poor approximation when n equals 0. But you'll see as I keep adding more terms, right, it's going to keep adding more and more to the sequence. And I keep adding more and I keep adding more. N is up to 40 now. 50. N is up to 75 here, 76. Look at how closely approximated these two pieces are. You can see that it does actually shy off here, but it's getting really close to that border of the 8 right there that we were talking about. And this piece right here is extremely well approximated. You can see it goes way far down for most of the shape on that one. So this is a really good approximation for a huge section of this particular function, and it is centered at 5, and it goes outward from there. Okay, so let's shrink it back down, and let's look at a different one. The 3 over 4 plus x squared. Right, is this bell curve looking shape? And here's a really poor approximation. Let's zoom in a bit. But almost immediately, right, that's the first term right there, n equals 1. It already has a nice shape that meets a good bit of the middle. Let's add a few more terms here, up to 20. And you can see it's spread pretty far by the time I add 20 of these terms into it. It's getting pretty close to the edges there of the 2 and -2 interval of convergence. So let's spread it really far out to 66, and you can see it is actually starting to get close to those boundaries, but it perfectly mimics this piece right here. Okay, and one more. I have the 9 over x squared plus 8x plus 11. We said that the center was -4. That's just the way it conveniently ended up. Again, here's your poor approximation. And let's add a couple of terms in there. And you can see at n equals 2, n equals 3, it's already closely matching this shape here. I don't have to actually add too many terms. I'll just get into the 20s here. And you can see it's all over on top of this thing. It has the shape down pat. And no matter how far I zoom out, you can't really tell the difference between the two. This one actually converged really fast to it. Which, of course, I mean, that's by no means the whole series. That's only 27 of the terms, but it already is a really, really good approximation of that particular function if you wanted your center to be -4. Notice I'm not getting these other two pieces in my approximation because of that interval of convergence. But if we were interested in them, we would just have to find a way to change our center to have some sort of region that included, what we were interested in. Okay? So I hope this helps you visualize what we're actually doing with these series by approximating shapes and values of these functions.